10 things you didn't know about Earth. Good advice from the 70s progressive band. Look around you. Unless you're one of the Apollo astronauts, you've lived your entire life within a few hundred kilometers of the surface of the Earth. There's a whole planet beneath your feet, 6.6 sextillion tons of it, 1 trillion cubic kilometers of it. But how well do you know it? Below are 10 facts about the Earth, the second in my series of 10 things you don't know. The first was on the Milky Way. Some things I already knew, and probably you do, too. Some I had ideas about and had to do some research to check, and others I totally made up. Wait. No. Kidding. They're all real. But how many of them do you know? Be honest. Mount Everest isn't the biggest mountain. The height of a mountain may have an actual definition, but I think it's fair to say that it should be measured from the base to the apex. Mount Everest stretches 8,850 meters above sea level, but it is a head start due to the general uplift from the Himalayas. The Hawaiian volcano Mauna Kea is 10,314 meters from stem to stern. Okay, bad word usagement, but you get my point. So even though it only reaches to 4,205 meters above sea level, it's a bigger mountain than Everest. The Earth has at least 5 natural moons. But not really. Most people think the Earth has 1 natural moon, which is why we call it the moon. These people are right. But there are 4 other objects at least that stick near the Earth in the solar system. They're not really moons, but they were cool. The biggest is called Croathan, pronounced MMPH lug, or something similar. It's about 5 kilometers across, and has an elliptical orbit that takes it inside and outside Earth's solar orbit. The orbital period of Croathan is about the same as the Earth's, and due to the peculiarities of orbits, this means it is always on the same side of the Sun we are. From our perspective, it makes a weird bean-shaped orbit, sometimes closer, sometimes farther from the Earth, but never really far away. That's why some people say it's a moon of the Earth. But it actually orbits the Sun, so it's not a moon of ours. Same goes for the other 3 objects discovered, too. Oh, these guys can't hit the Earth. Although they stick near us, more or less, their orbits don't physically cross ours, so we were safe from them. We live inside the Sun. Normally we think of the Sun as being that big, hot ball of light 93 million miles away. But actually, the Sun's outer atmosphere extends far beyond its visible surface. Our planet orbits within this tenuous atmosphere, and we see evidence of this when gusts of the solar wind generate the northern and southern lights. In that sense, we definitely live inside the Sun. But the solar atmosphere doesn't end at Earth. Auroras have been observed on Jupiter, Saturn, Uranus, and even distant Neptune. In fact, the outer solar atmosphere, called the heliosphere, is thought to extend at least 100 AU, that's nearly 10 billion miles. In fact, the atmosphere is likely teardrop-shaped due to the Sun's motion in space, with the tail extending tens to hundreds of billions of miles downwind. The Earth isn't an outlight spheroid. But we're not done. The Earth is more complicated than an outlight spheroid. The Moon is out there too, and the Sun. They have gravity, and pull on us. The details are complicated, say it yourself here, but gravity, in the form of tides, raises bulges in the Earth's surface as well. The tides from the Moon have an amplitude, height, of roughly a meter in the water, and maybe 30 centimeters in the solid Earth. The Sun is more massive than the Moon, but much farther away, and so its tides are only about half as high. This is much smaller than the distortion due to the Earth's spin, but it's still there. Other forces are at work as well, including pressure caused by the weight of the continents, upheaval due to tectonic forces, and so on. The Earth is actually a bit of a lumpy mess, but if you were to say it's a sphere, you'd be pretty close. If you held the billiard ball-sized Earth in your hand, I doubt you'd notice it isn't a perfect sphere. A professional pool player sure would though. I won't tell Alison Fisher if you won't. Ocean salt. Most of the salt in our ocean comes from rocks on the shores, mainly because rainwater, which is naturally acidic, breaks down the rock and distributes their components into the water. Seawater salt is so dense that if you were to dissolve all the oceans in the world and spread the remaining salt over all the land on Earth, you'd have a 500-foot thick salt layer coating everything. There are Mars rocks on Earth, and we didn't bring here. Chemical analysis of meteorites found in Antarctica, the Sahara Desert, and elsewhere have been shown by various means to have originated on Mars. For example, some contain pockets of gas that is chemically identical to the Martian atmosphere. These meteorites may have been blasted away from Mars due to a larger meteoroid or asteroid impact on Mars, or by a huge volcanic eruption, and later collided with Earth. Super-Earths. Earth has always been a curious place because it's only just barely far enough away from the sun not to get burned, but not so far that it freezes. Scientists have been searching through a number of exoplanets, planets that orbit another star other than our sun that happen to be in the habitable zone, not too hot and not too cold, just enough of both to sustain life as we know it. Since 2012, several super-Earths have been discovered considerably bigger than Earth, but still in the habitable zone. We've even seen a planet discovered this year that is roughly the same size, could theoretically sustain life and orbits a red dwarf. There's no telling if we'll ever find another Earth. That's a job left to the future generations. Rocks can walk. There exists a flat lake bed in Death Valley known as Racetrack Playa, in which rocks physically move from place to place, and it's not just small rocks, but ones weighing tens or hundreds of pounds. The theory goes that these ice-encrusted rocks are flooded by meltwater from the hills. This makes everything nice and slick, which, along with a hard breeze, allows the rock to travel. Even really small bodies can have moons. It was once thought that only objects as large as planets could have natural satellites or moons. In fact, the existence of moons, or the capability of a planet to gravitationally control a moon in orbit, was sometimes used as part of the definition of what a planet truly is. It just didn't seem reasonable that smaller celestial bodies had enough gravity to hold a moon. After all, Mercury and Venus have none at all, and Mars has only tiny moons. But in 1993, the Galileo probe passed the 20-mile-wide asteroid Ida and discovered its 1-mile-wide moon, Dactyl. Since then, moons have been discovered orbiting nearly 200 other minor planets, further complicating the definition of a true planet. The Earth is getting more massive. Sure, we're safe from corrosion, but space is littered with detritus, and the Earth cuts a wide path, 125 million square kilometers in area, actually. As we plow through this material, we accumulate on average 20-40 tons of it per day. Note, your mileage may vary. This number is difficult to determine, but it's probably good within a factor of 2 or so. Most of it is in the form of teeny dust particles which burn up in our atmosphere, what we call meteors or shooting stars. But doesn't meteor sound more sciencey? These eventually fall to the ground, generally transported by raindrops, and pile up. They probably mostly wash down streams and rivers and then go into the oceans. 40 tons per day may sound like a lot, but it's only 6 times 10-21% the mass of the Earth. In case I miscounted zeros, that's 2 times 10-26, 6 times 10-21 times the Earth's mass. It would take 140,000 million, 450,000 trillion years to double the mass of the Earth this way, so again, you might want to pack a lunch. In a year, it's enough cosmic junk to fill a 6-story office building, if that's a more palatable analogy. I'll note the Earth is losing mass, too. The atmosphere is leaking away due to a number of different processes. But this is far slower than the rate of mass accumulation, so the net effect is a gain of mass.